All right, well, we can get started then. Hello, everyone. If we haven't talked, I'm Jake. I'm doing my teaching practicum for this class. A few notes. I will probably be asking you people to talk to your neighbor today. So if you don't like that, I'm sorry, but luckily you're only going to have me teach 2 lectures. And also, I had a nosebleed about 30 minutes ago, so if my nose starts bleeding again, somebody just yell at me, please. Cool? Everybody good? All right, we're going to start with the spherical coordinate system today, doing separation of variables. And so the 2 things I want to mainly answer here are how are we going to determine the elementary solutions, norms, and eigenvalues in the spherical coordinate system, and then how do we solve these problems. So exactly the same that we've already done with Cartesian and cylindrical coordinates, just spherical now. Everybody good? All right. So we're going to start with just drawing our sphere, get our coordinate system down. So we're going to have our 3 axes, right? So first we're going to have R, right? Let's see if I'm doing this right. So R is just going to be our radius. We're going to have our azimuthal direction, which is our phi, same as cylindrical. And then we will have our zenith direction, which is going to be our new one, theta. And so we're going to be using these 3 variables along with time to form our separation, our separated problems. And so with these, we can look at our Fourier's law for each of these individual components. So in the radial direction, we will have Q sub R double prime equals negative K dt dr. In our azimuthal, which is a horrible word, we'll have Q sub phi double prime equals negative K over R sine theta dt d phi. So if you remember from the very first homework when we were looking at our scaling factors, that's what this right here is going to be. It's our scaling factor for the azimuthal direction. And lastly, we'll have our zenith. Also, if you have any questions, you can just shout out. No need to raise your hand because I might not be looking up. In our zenith direction, we will have Q sub theta double prime equals negative K over R, partial derivative of temperature with respect to theta. Very good. Okay, so then we're going to take our Fourier's law and we're going to plug it into our governing equation for heat conduction. So we'll have this big, long equation, which is the second partial derivative of temperature with respect to the radius plus 2 divided by the radius of the partial derivative of temperature with respect to the radius, plus 1 over a radius squared, sine theta, partial with respect to theta, of sine theta, partial derivative with respect to theta, plus 1 over r squared sine squared theta, partial derivative, the second partial derivative with respect to phi, plus our generation term, divided by our thermal conductivity, equals our transience term. Is that all good for everybody? Feeling familiar? I'm just waiting to make sure your pen stopped writing. All right. And so this equation is not very easily separated or easy to work with when we're trying to solve problems. So we're going to make a couple substitutions. So our first is that we're going to say mu is equal to the cosine of theta, in which this is bounded from -1 up to +1. And what this is doing right here is we're going to map theta, which is our zenith direction here, from 0 down to pi right here. Okay? And so then doing this, when we plug it back into the equation, we're going to now have it in the form of the partial derivative of temperature with respect to R plus 2 over R. This first part's just going to be the same, plus 1 over R squared, partial derivative with respect to mu of 1 minus mu squared, partial with respect to mu, plus 1 over R squared, 1 minus mu squared, second partial with respect to phi, plus our generation term is equal to our transient term. So all we've done here is we've replaced our zenith direction with mu. We'll see why this makes it easier as we get to the problems later on. Give me like a thumbs up if you're done writing. Okay. All right. The second substitution we're going to make is we're going to say V of R mu phi and time is equal to the square root of R times T in R mu phi and time. And so when we plug this back into our governing equation, we'll now have something of the form the second partial differential of V with respect to R plus 1 over R partial with respect to R minus V over 4 R squared plus 1 over R squared partial with respect to mu of 1 minus mu squared partial with respect to mu plus 1 over R squared. Golly, this marker's a little thick to write with. Can you all read this still okay? All right. Partial of V with respect to phi plus our generation term, which is now going to be multiplied by the square root of R, is equal to our transient term. Okay, I'll make a note that this is only for transient multi-dimensional problems. And with spherical, we're going to have some unique cases depending on the variables we'll use. So in the book, you'll want to look at table 5-1. And those will kind of be your cheat sheet for which substitutions we're going to make. In general, we're always going to make the mu substitution. That'll make it easier. Yeah?
So the dd mu, is that 1 over R squared?
dd... Yes, that's 1 over R squared. Yeah. We'll always make the mu substitute. Yes?
The substitutions we just made, is that only applicable for this case, this multidimensional transient?
Yeah. So right now we're doing the most general case, which is going to be all of the variables.
Okay.
And so this specifically is going to be for multidimensional transient. We'll see as we get later into the lecture, you'll see different problems where we make a slightly different substitution.
Okay.
But generally, we're still going to have some form of this. Okay. All right. Let's keep going. Oh, yes. So we also are going to need to carry out this substitution in the... Oh, thank you so much. Is that better? Yeah. Okay, wonderful. We'll need to carry out the substitution in the initial condition as well as the boundary conditions. But if we're doing this generically, we're not going to have those. So V of R mu phi and time is equal to 0. It's going to be equal to 1 over the square root of R times our initial condition, if that's F in R mu and phi. Okay. So as we're going to move forward, we're going to start separation of variables, and we're going to assume the form that V of R mu phi and t is equal to the multiplication of some function dependent on R, some function dependent on mu, some function dependent upon phi, and some function dependent on t. Okay.
Say the initial condition is 1 over the square root of R, but at the top we had the definition as multiplied by the square root.
I think I might have that wrong in my notes. That should just be R to the 1/2. Yeah, I think so. Ask me again at the end of class, I'll check in the textbook, but I'm pretty sure that that's just a typo in my own notes. Okay. So as with the other problems in Cartesian and cylindrical, we're going to assume that it's a homogeneous problem, no internal energy generation, we're going to have constant isotropic properties, and the separation of variables in the form that I just wrote. So when we substitute that separation of variables, we're going to get a rather long equation again, which is going to be 1 over cap R, and these are no longer partial differential equations of the second derivative with respect to R, 1 over R, d cap R, d lowercase r, minus cap R over 4r squared. So that'll be our R term. Plus, when we look into our mu term of 1 over lowercase r squared, cap M, derivative with respect to mu of 1 minus mu squared, derivative of m with respect to mu. That'll be our zenith direction, plus 1 over r squared, 1 minus mu squared, cap phi, with our second derivative of cap phi with respect to phi is equal to 1 over alpha cap gamma d gamma dt. Okay. So what do we do here now? Sorry?
Separation constant.
Equals lambda squared? All right. Is it plus or minus lambda squared? Who thinks it's plus? Who thinks it's minus? All right, great. It's minus. So we want this to be exponentially decaying with time. So this is going to be our first separation constant, lambda. We're going to take this side of the equation right here, and we're going to give us d lambda dt plus alpha, d gamma dt plus alpha lambda squared, gamma of t equals 0. Okay, you've all solved this a million times by now. What's the solution?
Negative alpha lambda squared t.
Yep, negative alpha lambda squared t. Everybody nods, thumbs ups, still going good? Okay. So now we have our time separated out. We'll now consider our spatial variables. So we have 1 over r. Let me write this a little bit quicker. So we've already written it a couple times now. dr minus cap r over 4r squared plus 1 over r squared cap m, derivative with respect to mu of 1 minus mu squared dm d mu plus 1 over r squared 1 minus mu squared cap phi, second derivative of phi plus lambda squared equals 0. And since we are assuming in a transient problem that the non-homogeneity will be given by our time dependent, our initial condition, we'll expect all three of our spatial components to have homogeneous boundary conditions. But if we want to separate this, we're going to have to force the characteristic value problem. So we're going to need some sort of special separation constant. I'll give you a second and talk with a neighbor. Can I separate this equation as is? What would I need to change to do it?
So cancel out the 2 ways there. Yeah. And then you need to do that again. It's twice. But it's much more
If you're not talking with anybody, do you have the answer?
Yeah. No. Oh yeah, you have to keep. You're just gonna have the r squared attached to the thing you can't. You want to keep the r squared was attached to yeah, but if you want to make it DD, how are you going to take this to the other side? Multiply the whole thing by
Maybe multiply by the neighbor's fee first, and then deal with
take it to the other side.
All right, bring y'all back. Can we separate it?
Not in its current.
No. Okay. Does anybody know how we're going to fix this? Yes, Fadi.
Multiply both sides by r squared and 1 minus mu squared.
Okay, yes, we're not going to get to 1 minus mu squared yet. But to get this separated, we're going to multiply this by r squared. Okay? So when I do that, I'm going to have to write this all out again. We're going to get r squared over r, second derivative of cap r with respect to r, plus 1 over r. This is the same exact term that was there before, just with the r squared on the outside. Minus, oh, that's wrong. Plus, I'm going to put the lambda squared r squared here. You'll see why in a second. We're going to bring the rest to the other side of the equation to make it a little bit easier as we go forward. D mu of 1 minus mu squared, derivative of m with respect to mu, minus 1 over 1 minus mu squared, cap phi, second derivative with respect to phi, equals some separation constant. Okay, so you see how we went from here, okay, where we can't separate here, right, because we've got an r squared term with our m direction and an r squared term with our phi direction. So we multiply by r squared, those are going to go away. Now each of these is separated from r, and r is unique. Okay? We're going to do something a little funny here, which, how many people watched the videos that I sent out yesterday? 2, 3. Body, you just watched it. That doesn't count. All right. We're going to do something a little different. We're going to set our separation constant as n times n plus 1, where n is going to be bounded to integers. You'll see why as we go forward, or if you're familiar with Legendre polynomials by now, you'll understand. So now we're going to solve this in the r direction. So I'll have d2 r dr2 plus 1 over r dr minus r over 4 r squared plus lambda squared cap r minus n times n plus 1 over r squared cap r is equal to 0. We can rewrite this now as the second derivative of r with respect to r. Hopefully I'm not saying r too much that you're never going to like hearing that letter again. Dr plus lambda squared minus n plus 1/2 squared over r squared times r is equal to 0. Does this equation look familiar to anybody? Just Body? Anybody else? Thumbs up if you've seen this equation before? All of you have seen this equation before if you've been in a lecture. Yeah. So this should be it's not Cauchy, but this will be our Bessel function. Of order what? N plus 1/2. Yes. So our solution, just like with the cylinders, is going to be our Bessel functions, which you can find in appendix, I think it's 4 in the book. So we can go directly to the solution of r is going to be equal to C2, our Bessel function of the first, or of order n plus 1/2 lambda r plus C3, our Bessel function of the second kind of order n plus 1/2 lambda r. And if you want to know how you get from our ODE to the solution, you can watch the YouTube videos that I sent. Okay? So great. Now we have our gamma and we have r. We can move on over to our last two variables. So what we have, if we now, as Fadi mentioned earlier, we're going to multiply by 1 minus mu squared to now separate out m and phi. We'll have 1 minus mu squared over m d mu of 1 minus mu squared dm d mu plus 1 minus mu squared of our newest separation constant, n times n plus 1, is equal to negative 1 over cap phi, the second derivative of cap phi is equal to another separation constant. Also, if this gets too crooked, somebody just shout out at me that I need to turn it back flat. Okay, everybody see this? Got where it's coming from? Okay, we're going to set this separation constant as m squared. Okay, does anything here look familiar to you? Talk with a neighbor if you need. All right. Who has my solution for the phi direction? Cosine? Of? M? Phi? Sine? Of m phi? Am I missing anything here? Or constants, right? C3 and C4. Okay. Same exact solution that we have for Cartesian.
C4.
Thank you. Yes, C4 and C5. Okay. We've all seen this equation before. 100 times. All right, and so lastly, as with cylinders, we're going to restrict m has to be with 2 pi periodicity. Who remembers what that means? Yes, the derivative. Yes, so the temperatures are the same at 0 and 2 pi, because as we go around a whole sphere, 2 pi radians will be back in the same spot. Okay, so that's what our 2 pi periodicity means. And so m can equal 0, 1, 2, etc. All right, now our last variable. How am I doing on time? Oh, going a little slow. All right. 1 minus mu squared dm d mu plus n plus 1 minus m squared over 1 minus mu squared times m equals 0. Now, if you watch the videos, you'll notice this is called the associated Legendre equation, which conveniently has its own solution, and it's going to feel very similar to our Bessel functions. So our solution in the mu direction is going to be C6 times our Legendre function or Legendre polynomial of the first kind of order n to m of mu plus C7. And then we'll have the same thing in the Legendre polynomial of the second kind. And these would be Appendix 5 if you want to look up any of the values. Okay. And so lastly, as we go forward, again, we're going to sum up or multiply all 4 of our separated functions together to get our solution for V. And then our boundary conditions are going to give us our eigenvalues and eigenfunctions as normal. And then our general solution of V is going to be the summation across all of our eigenfunctions. Okay. We good with our general solution? All right. Great. So we're going to go to an example. And this is from a different textbook, so you have an extra example that's not in the textbook. I'm going to give you a sphere of radius r0 and a surface maintained at an arbitrary temperature distribution in the mu direction. We'll have constant properties and no generation. So, over-rotated that time. So if we're going to start from our original equation, second partial differential with respect to the radius, plus 2 over r, derivative with respect to the radius, plus 1 over r squared, d mu, 1 minus mu squared, dt d mu, plus 1 over r squared, 1 minus mu squared, d2t, that is a t, d phi 2 plus g over k equals 1 over alpha dt dt. Okay, that's our overall equation again. We have no phi direction in this problem. It's going to be uniform across there. We have no generation, and it's steady state. I don't think I actually told you that, but it's going to be a steady state problem. So, we have 3 boundary conditions for this. 1, BC, 1 is t as r approaches 0 is finite. Do you all know what t as r approaches 0 is finite means? All right, somebody tell me. What does it physically mean?
You can have infinite
Symmetry?
You can have infinite temperature at your center. Symmetry.
Can't have infinite temperature at our center. Essentially, that throughout the entire sphere, it's all a real value of temperature. Okay. Second boundary condition is going to be our non-homogeneous, which is t at r equals r naught for all of mu is equal to some function in mu. And our last boundary condition is t of r as mu approaches 1 is finite. Okay. Those are our boundary conditions. And so we're going to separate this problem out into, this should be mu, into a function in r and a function in mu. So when we do that, we'll end up with r squared over cap r, second derivative of r plus 2 over r with the derivative of r is equal to negative 1 over cap m times d mu of 1 minus mu squared dm d mu. This is going to equal plus or minus our separation constant, n times n plus 1. All right. Should it be positive or negative for us? Positive. Okay, why?
We have non-homogeneous R.
Yep. Exactly. So we have non-homogeneity in the r direction, so this is going to be positive to match with our r. So if we then split this up and we're going to solve, first I'm going to do it in the mu direction times 1 minus mu squared d cap m d mu plus n times n plus 1 cap m equals 0. This is going to be known as our Legendre equation. Once again, if you want to see the solutions, you can talk to someone in the math department or you can watch the YouTube videos because I'm not the mathematician here. But this is going to give us m, let me write that clear, m and mu is going to be equal to some constant times our Legendre equation of the first kind of order n, evaluated at mu, plus another constant, our Legendre equation of the second kind of order n, also evaluated at mu. Now, we can apply our boundary condition 3, which is t as mu approaches, I think this actually should have been 0 on the previous page, if I'm not mistaken. I'll check that later. Is finite. I think it's as approaches 0. This will give us C2 is equal to 0 because it's Q of mu is equal to 0 will give us, I believe that's a negative infinity. You can find that again in Appendix 5. This is going to happen for pretty much every single case we have. We'll just be left with the Legendre polynomial of the first kind. Okay. So then, if we move to the other side, and we're looking in the r direction, we'll have r squared times the second derivative with respect to r plus 2r dr minus our separation constant, r equals 0. Now this equation, who was saying Cauchy earlier? Is that you? Yeah. So this will be our Cauchy equation, which you can find on page 133 in the textbook. But our solution to this will be equal to some constant times r raised to the nth power plus another constant times r raised to the negative n plus 1. Okay. So we're going to apply boundary condition 1 here, which is t as r approaches 0 is finite. So which constant is going to go away? C4. Yep. C4, therefore, must be equal to 0. Okay, so now if we bring this all back, we're going to have t as a function of r and mu is equal to the multiplication of our separated functions r and m, we're going to, this actually probably shouldn't be summed yet, is going to be equal to C1, C3, R to the n, and P to the n mu. Actually, no, I think that should be a summation. Yeah. Sorry. We're going to sum this from n equals 0 up to infinity. We're going to sum across all of our eigenvalues. Keeping with this? And C1 and C2, C3 multiplied together, we can write as Cn. All right, as we move forward, so our function of t is equal to our summation from n equals 0 up to infinity of Cn, r raised to the n power, and our Lagrange polynomial of the first kind of order n evaluated at mu. We're going to apply our boundary condition 2, which means t of r, losing myself, r equals r naught. It's going to be comma mu equals some function in the mu direction. It's going to equal our summation from n equals 0 to infinity of Cn r naught raised to the nth power times our Lagrange polynomial. Okay, so what do we have to do here to solve for a constant? Apply orthogonality. So we're going to multiply this by our integral from mu equals -1 to 1 of our Lagrange polynomial of the first kind of order q, we'll say, where q is arbitrary, times d mu. What this is going to give us is that when n is equal to q, we'll have some norm of, should be n, and then when n is not equal to q, this will give us 0.
Is that -1 on the integral?
This -1?
Yeah.
Yeah, it's -1. Because we're dealing with
-1 to
-1 to 1. Sorry. Yeah.
Is the weighting function in mu just 1?
Yes. Good here? Okay. All right. So then we will have our integral from -1 to 1 of our function in the mu direction, piece of order q evaluated at mu, d mu is going to now equal our integral from -1 to 1 of Cn r naught raised to the nth power, Pn of mu, and Pq of mu, d mu. Where did our summation go? TK?
It goes away when we decide to make n equals q.
Yes, so it's going to go away with our orthogonality. We can then solve for a constant, which is going to equal, let's see if I can write this without making a mistake, or integral f of mu p sub n of mu d mu over r not raised to the nth power for integral from -1 up to 1 of p sub n mu squared d mu, where this bottom half, the norm is going to give us r naught raised to the nth power times 2 over 2n plus 1. So then when we put this all together, we'll finish with t of r comma mu equals 1 over 2 times our summation from n equals 0 up to infinity of 2n plus 1 r over r naught raised to the nth Lagrange polynomial of the first kind of order n mu times our integral -1 up to 1 of f, and we call this mu prime here so we don't mix up our integrals and functions, times our Lagrange polynomial at mu prime by du prime. All right, that's our solution. Yes?
For Cn in the numerator, why is it Pn instead of PQ?
It could be PQ, but see, when we get rid, or when we apply orthogonality here, we'll see n is equal to q, we'll get the norm. So then when we go through our summation and this comes out, it becomes synonymous, right? So every time, the only time we're evaluating is if n is equal to q. So you could write it as q, it'd be the same thing. Yep.
So where does the summation even come from in this case? For the Legendre form?
It's
Because you have mentioned only 3 boundary conditions for the question, even though it's 2D problem. There are only 3 boundary conditions. So
I'm going to need to check in the textbook for that one. I'll make a note. I will send an announcement after
I think
class.
it's because of the periodicity.
Yes.
0 and 2 pi, they're the same things, and so those are the same boundary conditions.
Yeah.
I think, but you might want to check because
Yeah. I think that is correct. But I'll make a note and I'll send a Canvas announcement out later. Double check. All right. So everybody good with this problem? All right. I'm going to do one last one. I'm going to try and get through this in, we have got till 3:15? Okay, we got time. All right, and this is going to be example 5.3 in the textbook. It's going to be transient in the r and the mu directions. We're going to apply a different substitution here. So we saw the v substitution at the beginning for generic. Instead here, we're going to apply our u substitution. Which if anybody did the problem on the board, this will come in handy in a moment. All right. So if I have a sphere of radius b, initially, can't seem to spell that word right now. Initially, at some temperature that is a function of r, and then for time is greater than 0, r at b, so our outer boundary condition, is going to be a convective layer with coefficient h into a body at t equals 0. Okay, so I'm going to draw this out for you, and then I want you to write our equation. So t is a function of r. And out here we've got h comma t equals 0. And our radius is equal to b. Yep. All right. So take a couple minutes, talk with your neighbor. I would like you to write sub out our governing equation. Give me the boundary conditions, and give me the initial condition in mathematical form. Yeah, so that's at Yeah, so I think that's what it is. It's technically the fourth boundary condition is the 2 pi periodicity. This is where the summation comes from. Just kind of skip that part because for spheres we're always going to have it. It's just kind of assumed, but I need to double check in the book on that.
Generally does like 2 boundary conditions temperature and force.
Yeah, right. Yeah, so they're synonymous. Yeah, so it would be in the feed direction. That specific problem.
I guess it's still.
There's nothing about that. So you would still have.
Initially at the temperature function.
The early ones.
And
And then you can go from there, yeah.
It's finite. It's last boundary condition with this. It's finite.
The governing equation up there.
This is 0, oh, right, okay, yeah, same thing, we're just functional.
Well, it would be still.
Yeah, it should be the same one.
Yes, you are. Yeah, that is so. Well, are you including the new condition of boundary? Yeah. Yeah, like, so I get
See anything out there in the mu direction?
class clowns over
Yeah, so that comes in your boundary conditions. You just have to have the.
And we're just gonna take.
All right, we can come on back. All right. This is my governing equation here. What terms are we crossing out? Phi. Yep. Generation. What else?
That's it.
That's it. You sure? Mu. Yeah, I lied here. There's actually nothing unique in the mu direction.
No.
You all fell like sheep. Didn't see it. There's nothing unique in mu. None of the boundary conditions have it. So we're going to have, d partial derivative of temperature with respect to r plus 2 over r equals 1 over alpha partial with respect to time. Okay, how many boundary conditions do I have?
You need to.
3.
Just 2.
2. Yeah, all right, so give me one boundary condition.
D of r goes to 0 is finite.
Okay.
And minus.
No. Somebody other than Fadi, give me another boundary condition.
T of r equals b is equal to negative k partial of t with respect to r at r equals b.
Yep. Great. And somebody give me my initial condition.
F of r is equal to t for time equal to 0.
Cool. Everybody got that? All right. We're going to do two things with this. First is this equation is not the easiest to work with. We could, but we can rewrite this now as 1 over r, the second derivative with respect to our radius of rt is equal to 1 over alpha partial with respect to time. Okay, that's a little easier. And now what we're going to do to make it even easier is we're going to define a new variable, which is u, for r and t is equal to r times t of r and t. Okay, so much like we did with v at the start of class, we're doing this with u. If anybody did the problem behind me, you're in luck, because we're about to do that exact thing. So, actually, what?
Why would we do that?
Why would we do that? You'll see. Be patient. Take 3 minutes, let's say, and I want you to rewrite the boundary conditions, initial condition, and governing equation with this transform. And you're more than welcome to talk with your neighbor if you want. Also, if any of you brought the textbook, it's just in there. You can. I'm telling you not to.
Yeah.
Trust. No trust.
Which one?
Oh my god, it doesn't happen.
Gonna make things nice and easy.
Is that the right way?
No, it's always gonna be.
I have don't let me say your proposal.
You said it got rid of something, Avery?
I didn't do that.
You are commanding
You got rid of the RT
the last
side, the R side. So it makes it not easier.
that we are multiplying with that. Yes.
I think I know what you're trying to do.
What I'm trying to do. I didn't come up with this stuff.
You can't trust it.
I know it's gonna.
Somebody figured this out long before we were born.
Yeah, fair.
All right. Governing equation. I'm just going to kind of move along because we're running low on time and I want to finish the problem. D over, or the partial derivative of u with respect to r is equal to 1 over alpha partial with respect to time. So this right here is why we're making this substitution. It's because our whole 1 over r term is just going to disappear. It's going to make it really easy to work with. All right, and then BC1 will now become u of r equals 0. It's equal to 0. BC2 is going to be partial derivative of u with respect to r at r equals b plus h over k minus 1 over b times u of r equals b is equal to 0. I'm going to shorten this and just call this capital K. And then our initial condition is going to be u of time equals 0 equals r times f of r. Okay. So we're going to, let's see. We're going to assume separation of the form u of r and t is equal to cap r and gamma of t. You think you can all solve this problem from here?
Yeah.
All right. We're going to take 5 minutes. Don't actually solve it, but write out all the steps. You don't need to solve it because you all have access to the textbook, so you can see that later. But write out all the steps, work with a neighbor, and I'll go along and see how you're doing. Well, that sounds like a bad space to work in a lab. What's the last thing we're going to do? Yep.
ODE is, it's a,
It's not a. You split these guys.
oh,
No, you're not.
oh, it's just time, yeah. I'm just so tired. I saw a DR post. Yeah.
Good. How you doing? she took this class.
So you get the sign of the cosine.
Just math. You doing all right? Just write the steps out. If we don't have enough time to solve the whole problem, if you are on the right track. Yep.
You can like catch the right train, so it doesn't go back. Yeah.
Yeah. Exactly. You got it.
You're just gonna have a poster here, so we're talking about posters.
The same.
He's standing for the little one.
All three coordinate systems.
No, it's not. It's not.
Pattern out in the book, the math is kind of easier.
You get to be.
Yeah, that's
Pretty tough. Yeah, I did that for undergrad in your textbooks. Just such an easy solution without muscle.
That's an undergrad textbook?
It was for the what's it? Like what concentrations were you doing? Like my research.
right. You have Cartesian,
Gotcha.
cylindrical, and then you have spherical. Like you have the chart. What I comes kind of the solution to get is.
It's because we already finished. We got dynamic duo right here. I didn't solve it. You told me not to solve it. You told me to write some. So you solve the first OD to get the exponential, solve the second OD, get the cosine sine, then you work on boundary condition 1 to eliminate
I guess because
one of your
it's not
constants,
power
and
times
then use boundary
so it
condition
like
2 to define your eigenvalue, and then you combine your
like if this is
constants.
finite, it goes by IR, and R is 0, that's
Your IC.
I switched to material science for my PhD.
Yeah, oh, I prepped up on that. Oh, and then you sub back the UR. We do, yeah.
All right, anybody still working? All done? All right, what's the first step? Shout it out.
Finding time.
Separate the variables, right. I already did that for you. Separate the variables, okay. Then what's next? Speak up.
Put it back into the general equation.
Yep. Substitute in. Okay, and then what are we going to do?
Equal to a constant.
Yep. We need our separation constant. Yep, that'll be our negative lambda squared. And then what do we do? Solve. R and gamma. Then boundary conditions. Did anybody actually like do the math and figure out which conditions?
Yes, the one with cosine.
Yep, okay.
Depends on you.
Yep, cosine is going to disappear. And if you did that, did you get my eigenfunction?
Lambda
Yes.
cotangent. Lambda E.
Exactly what he said.
Lambda n cotangent.
Lambda ND
Well, he lives with me, so he has to get this.
equals negative capital H. Never mind.
Negative.
All right. Okay, and then what do I do?
Apply your initial condition.
Initial condition, what does that give me?
Function you can apply orthogonality to.
Yes, and then I need to apply orthogonality.
Solve for CN.
And this is going to give me our Cn. Did any geniuses get Cn?
Yeah.
Okay, I'm not going to write it down. That's a lot of work. All right.
Minus
And then what?
Put it back together.
Put it back together.
Okay.
the temperature profile.
Oh,
So then
R.
U equals R and gamma. And T equals RU. Congratulations, you all solved it. I don't know.
Divided by C.
Divided.
Divided.
Yeah, sorry. You're right. Hey, I'm not infallible. Okay, U over R. And so then I'll say our actual function is going to be equal to the sum from n equals 1 to infinity of Cn lambda n exponent negative alpha lambda squared t sorry, this lambda n shouldn't be here. That was skipping a step. Sine lambda n r over r. That'll be our function. You can check the solution in the book. It's example 5.3. You can look through the work and actually solve it out. But if you know all the steps, it's the same as Cartesian and cylindrical. Yes?
Why is this going from n equals 1 to infinity and 0?
That is a great question.
N equals 0.
Lambda 0 equals 0, it becomes a trivial solution.
Yep, that would be trivial. All right, I will field any questions for the next 4 minutes. But if you don't have any questions, or while you ask questions, I'd love it if you would take out your phone, go to Canvas on the announcements, and click on my feedback form, because I need the feedback. I'm doing the Tech to Teaching certificate, so I'd appreciate any comments, even mean ones. It's anonymous. Somebody else will fill it, read through it, and give it to me.
So let's give Jake a hand, by the way. It's fairly courageous to take a grad class for teaching practicum.
Any questions? Was that good? In this problem? Or the V substitution or the U substitution?
This substitution where U is equal to T time.
Right. So before we had this, right, this 1 over R in here and then an RT over here. This was a little nasty to deal with. So when we apply this substitution, our ODE conveniently becomes this. It's much easier to work with and solve through. Again, table 5.1 in the book will tell you exactly what substitutions you should make for every single problem. Because, you know, the exams are open book. I might bookmark it. Any other questions? Somebody was asking on the summation. We got 2 minutes. Let's see. Yeah.
Yeah. The Falcon.
See what you guys like the movie. We were in a TV show. No, yeah, I can show you. Where is it?
Yeah. It's at the library.
Regarding the summation term,
Yes, that's what I'm trying to figure out.
but non-trivial solution at n equals 0 equate the eigenvalue in terms of n goes from 0 to such that 0 to 2 pi condition, curiosity condition is met. So it's like, like pi n over b or something like that. And it's validated later on. We have t or something, and we put 0 and it's a non-trivial solution.
Is that okay if I just?
Who was asking about the summation term? Look at example 5.1 in the book. You'll see it. It's pretty similar, just I did a whole sphere, the book does a hemisphere. It's the same thing. All right, it's also 3:15. Y'all are more than welcome to leave.